stress, and strain curve. Understanding this curve helps engineers design safe and strong structures. When a material is subjected to a gradually increasing load, we can plot stress-strain curve. Strain at x-axis and stress at y-axis. The shape of the curve tells us how the material behaves under tension. Let's go through the different regions of the curve for a ductile material like mild steel. At point A, proportional limit. In this region, OA, stress is directly proportional to strain. Follows Hooke's law. If you remove the load here, the material returns to its original shape. The line is straight in this region. Slope of this line is equal to Young's modulus of material. At point B, elastic limit. The elastic limit is the maximum stress that can be applied without causing permanent deformation. If you remove the load before this point, the material returns fully to its original form. Once this limit is crossed, the material enters the plastic region. After the elastic limit, the material begins to yield, permanent deformation starts. The stress remains nearly constant even though the strain increases. It often has upper yield point C1, where yielding starts. Lower yield point C2, where yielding continues steadily. Reason for upper yield point. In mild steel, tiny atoms such as carbon or nitrogen can hold dislocations in place, making it harder for them to move. When the force becomes strong enough to break these bonds, the dislocations move suddenly, causing a quick drop in stress. After the upper yield point, the metal keeps stretching at almost the same stress level, forming a flat part on the stress-strain curve, called the yield plateau. After the lower yield point, the material strain hardens, and the curve rises again. As deformation continues, the material becomes stronger and harder, but less ductile. Stress must increase to cause further strain. Strain hardening is the process where a metal becomes stronger and harder when it is stretched, bent, or deformed permanently. When a metal is deformed, many dislocations form and move. As more dislocations appear, they start to interfere with each other, making it harder for the metal to deform further. The ultimate stress point is the point on a stress-strain curve where a material reaches its maximum stress before it starts to neck or weaken. After the ultimate stress point, the material cannot uniformly stretch anymore. Necking is the stage where a localized reduction in the cross-sectional area of a material occurs. Most of the deformation then concentrates in this narrow region, not along the whole specimen. Finally, the material breaks at point E. Yield strength. In most engineering practice, the lower yield point is taken as the yield strength, because it represents the stable value of stress at which plastic deformation occurs. Stress at lower yield point is nearly equal to stress at elastic limit. Yield strength is a critical design parameter. Engineers ensure stresses stay below this to avoid permanent deformation. The ultimate tensile strength is the maximum engineering stress that a material can withstand before failure in a tensile test. The elastic region is the part of the stress-strain curve where the material returns to its original shape and size after the removal of the load. The plastic region is the part of the stress-strain curve where permanent deformation occurs. If the load is removed, the material does not return to its original shape completely. Toughness, in a stress-strain curve, represents the ability of a material to absorb energy before fracture. It is the total area under the stress-strain curve. It indicates how much energy per unit volume the material can absorb before breaking. It combines strength and ductility. Engineers use the stress-strain curve to choose materials that can safely withstand the expected loads. Structural steel is chosen for bridges. Aluminium is used in aircraft. The elastic limit, yield strength, and ultimate tensile strength guide which material best suits the job. Thank you for watching.